You are given a parallel plate capacitor and asked to determine the capacitance. The plate spacing is D, and the region between the plates consists of two different materials. One material has a permittivity of epsilon sub 1, and the other material has a permittivity of epsilon sub 2. For a surface area of S1, the material between the plates is material 1, and for the rest of the plate area S sub 2, the material between the plates is material 2. In this class, you do not use any circuits concepts to solve these problems. If you use circuit concepts on an exam, you'll get 0 credit for the problem. Some of these problems are very easy to do using circuit concepts, but that's not the reason I don't want you to use them in this class. Approaching these problems from fundamental concepts will result in a greater understanding and mental models of capacitors, capacitance, and dielectrics. The capacitance is the ratio of the charge on the capacitor to the voltage across it. So we're going to apply a voltage, figure out the corresponding charge, and take the ratio of that charge to the voltage we're applying. The voltage across the capacitor is equal to minus the integral from d to 0 of E dot dl. You have to get this result no matter what path you take, whether you go through material 1 or material 2. So the electric field intensities must be the same in the two materials. With different permittivities, you'll have different polarizations in the two materials for the same electric field intensities. If the permittivity of material 1 is greater than the permittivity of material 2, that means the charge density on the capacitor plate adjacent to material 1 will be greater than the charge density on the plate adjacent to material 2. Let's look at the mental model you should have to make these conclusions. Here we're looking at lines of electric field intensity. Electric field intensity begins on positive free charge or positive bound charge and terminates on negative bound charge or negative free charge. The gaps I've placed here are just for illustrative purposes so that I can draw the electric field lines between the capacitor plate and the dielectric. In reality, there's no gap here. For simplicity, I've drawn the figures such that the cross-sectional areas of the two dielectrics is the same. To indicate the same electric field intensities in the two materials, I do that with the same number of electric field lines in the two materials. Since material 1 has a higher permittivity than material 2, for the same electric field intensities, material 1 polarizes more, so there's more bound surface charge on material 1 than on material 2. That means more of the electric field lines emanating adjacent to material 1 will be terminated than in material 2, so you have to begin with more electric field lines, more charge density adjacent to material 1 than adjacent to material 2. Let me call this charge Q sub 1 and this charge Q sub 2. Electric flux density begins on positive free charge and terminates on negative free charge. The electric flux density field in material 1 will be the charge density on the plate adjacent to material 1, and it will be in the x direction. That charge density will be Q sub 1 over S sub 1. This result should be something you're comfortable with at this point, but if you're not, you can quickly go back to Gauss's law and draw a Gaussian surface around the part of the plate adjacent to material 1 and determine the electric flux density field. Similarly, the electric flux density field in material 2 is the charge density on the plate adjacent to material 2, and it's in the x direction, and that charge density will be Q sub 2 over S sub 2. The total charge on the capacitor will be Q1 plus Q2. Q1 is charge density rho sub S1 times area S1, and Q sub 2 is charge density rho sub S2 times area S2. The voltage drop is equal to minus the integral from d to 0 of E1 dx if you're going through material 1, E2 dx if you're going through material 2, and we know those both have to give us the voltage we're applying to our capacitor. So the voltage drop is just the electric field intensity times the spacing of the plates. The electric field intensities are just the electric flux density fields divided by the permittivities in the material, and we know that the electric flux density fields are just the charge densities on the plate. Since the electric field intensities in the two materials are the same, rho sub S2 is equal to epsilon sub 2 over epsilon sub 1 times rho sub S1. Let's now substitute this for rho sub S2 so we get our equation for Q just based on rho sub S1. Now that we have Q based on rho sub S1, let's obtain the voltage based on rho sub S1 so that we can divide our charge by our potential and get the capacitance of our structure. So let's substitute this term right here for our electric field intensity in material 1. We obtain our voltage then is equal to rho sub S1 over epsilon sub 1 times D. So our capacitance will be the ratio of our charge to our voltage across our capacitor. So making this substitution for Q and this substitution for V, we have this expression. We can divide the numerator and denominator by rho sub S1. Multiplying numerator and denominator by epsilon sub 1, we get epsilon sub 1 S1 over D plus epsilon 2 S2 over D for the capacitance of our structure. So here is our result. Let me call the first term C1 and the second term here C2. This first term is the capacitance of a parallel plate capacitor of area S sub 1, permittivity between the plates of epsilon sub 1, and plate spacing of D. Similarly, this second term is the equation of the capacitance of a parallel plate capacitor of cross-sectional area S sub 2, permittivity between the plates of epsilon sub 2, and plate spacing of D. So you can treat this structure as two capacitors in parallel, where one capacitor is this region and the other capacitor would be this region. So you could get this result very quickly using circuit concepts. Approaching this problem from fundamental concepts gives us a greater understanding and mental model for the charges involved, the resulting fields, and capacitance of this structure.